Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Today we're looking at geometry in context. All right, and you're going to see how it's not just the cold subject, maybe we used to teach it as. And we'll go through the day and hopefully you'll enjoy the day. So first of all, look at the syllabus and how the syllabus is going to work for the next couple of years till 2015. So you probably know already from your papers that you've looked at on paper 2, there's an option question. So ordinary level, so foundation level, question 4, ordinary level, question 5, high level, question 6. And that's split up into two parts, A and B. Now the part A comes from this section 2.1 of the syllabus. So the only part of the exam paper where that section of the syllabus will appear is in that question 4, 5 or 6, part A. The part B of that question comes from the junior cert syllabus. Okay, so that's how that question is split up. Does that make sense? So it's part A and part B. Part A comes from section 2.1 of the syllabus. Part B comes from their junior cert. Now just looking at that sort of the syllabus and this embedded nature that the syllabus works on. Right, so for 2012, 2013 and 2014, your foundation level. So all the foundation level can be asked, and that part A is the constructions 18, 19 and 20. For your ordinary level, now the embedded nature of the syllabus, they need to know the foundation level as well. So if your ordinary level, constructions 16, 17, 18, 19, 20 and 21, understand these terms, investigate and use these theorems. Now, in some subjects, they might, in terms of the terms, it says understand and use these terms. So it's not a word-by-word specific definition they're looking for. It's not like you got the third word wrong, you're going to lose all your marks. It's understanding. Does that make sense? So they're looking for understanding of these terms. Investigate and use these theorems. Do they need to prove any theorems? No. So your ordinary level students do not need to prove these theorems. It's just to investigate them and use them. Higher level. Now again, the embedded nature of the syllabus. So high level, you need to know all these constructions, understand and use all these terms, use these theorems, and then prove these theorems. So in terms of the geometry, there are 3 theorems that your high levels can be asked. 11, 12 and 13. But be careful. You may have a textbook. Obviously it's from a friend from 20 or 30 years ago. All right? In that textbook might be a lovely proof that you think is nice. Make sure it's been validated by either the SEC or the NCCA. Okay? So any proof you use needs to be validated by them. Okay? Now where can you get the validated proofs? In the syllabus or on the student disc. If you have a lovely one that you like, you think, well, this is nice, the students really like this one, it's a nice way of explaining it, send it to the SEC or the NCCA in order for the students to receive full credit for it. Okay? And again, that's how we can get, they're all already done out on the student disc for you to use. All right. Now, how do students learn geometry? So research has shown, okay, so it's not just, I was sitting down last night and came up with these ideas. studies, researchers gone on and developed to show these are the best ways that students learn their geometry. By discovering the ideas, hands-on, collaborating with others, okay? Now, so throughout today, you'll be discovering ideas. You'll be actually getting involved with your geometry. You'll be discussing with each other. You're not going to sit next to your partner and say nothing all day. You're going to be discussing your work and working together, and your understanding will improve. Okay? And we're going to try and work in real life. Okay? And communicate mathematically. That's what you're going to be doing with each other and with the group. Now, Dewey may have plagued you during your hitch dip. And it's true. And it comes with anything. Okay? Give the pupil something to do, not something to learn. So no longer will it be sort of Theorem Friday, where all of a sudden, we've got these 10 theorems we have to learn off. Let's just sit down and recite them all. That's your midterm homework. Okay, the theorems. That's what it would have been previously. Just learn them off and that's it. We're actually going to put them into context, okay, and understand them. Now, geometry isn't something that's cold. Geometry exists out there in the real world. So here's Thurman Park. So the gentleman who prepared this section, okay, big monster man. Okay, is there any geometry we see here? That's right. Now, a big part of today is you being involved. All right. If you sit there and say nothing, it's a really boring day. Okay. So let's have a look at this. Do we see any geometry? Let's have a look at this pitch. Do we see any geometry at all there? Any lines at all? What sort of lines do we see there? Parallel lines? Perpendicular lines? Okay, what sort of shapes do we see? Rectangles? Any other sort of shapes as well? What sort of shapes do you see here? Triangles, yes, so rectangles, triangles. Yeah, geometry is real. Generally, we see these shapes in an abstract sort of fashion. Okay? Geometry is there in the real world. Do you know this boy? Yeah, Ronan? Why is he up there? What does he do? Hey? Pardon? Right, so why? So what happens here? So what is it he does, Ronan does? Kicks. Okay, when he kicks it, what does he do? Steps back and steps to the side. And so how many steps does he take back?
4.
And then how many to the side? 3. What does that mean then when he runs to that ball? He takes a perfect 5 steps. Okay, goes back 4, the side is 3. Every time the same drill. Takes a perfect number of steps then. Okay. What do we see here? What shapes do we have here? Triangles, okay? Lots of triangles coming on. Any particular special type of triangle? An isosceles triangle. Right? They're not just abstract shapes that occur. So one of the things is saying, right, when we're doing geometry, students all have their mobile phones and they love getting them out in class. Let's actually make use of them for a change and say, look, your homework tonight is go and take a photo of some geometry. Go and take a photo of an isosceles triangle. Okay? Geometry does exist out there. Let's see what we can do with it. What geometry do we see here? Okay. What geometry? Right. This is a cross in New York. What do we see here? What shape do we have here? What's this shape? Yeah. So we've got 2 sides that are parallel. These 2 sides. So what shape's that? Trapezium. Yeah. And what sort of lines do we have here? Parallel lines. Then we've got lines crossing the parallel lines, haven't we? Okay, what do you call them? Okay. So we've got lots of lines going on, right? And here, right, these shapes are all what? Yeah, then they're all the same, all like similar shapes, okay? Now, what we've done for you with the constructions and the theorems, okay? We've got them onto 2 pages, pages 2 and 3. All right, so you see on page 2 and 3, we've listed it out so you have all your constructions, okay? And again, you'll see from the sort of embedded nature of the syllabus, your foundation level, your ordinary level, and then your higher level. All right. Now we've actually taken the numbers away from beside them because the only thing, we're not going to say, right students, we're doing Theorem 11 today. The only thing we do by numbers is painting. All right, so we're not going to teach these theorems of construction by specific numbers, okay? So there's your constructions broken down, and there's your theorems, okay? Now, you're going to get an image, a two-sided image, okay? And you have to apply theorems or constructions to this image. So what theorem or what constructions can we apply to the image in front of us? Okay, so pages 2 and 3. Okay, so in your pairs, what theorems or what constructions can you apply to the image in front of you?
Yeah, and the centre, there's one is the line bisectors, one is the angle bisectors, centroid, using one straight.
Right, so a couple of groups had this image. So what do we see in front of us?
Circumcircular and incircular.
Okay, so we had so first of all we had so it's 3 satellites. Okay, you'll see this image quite a lot. Okay, so what sort of triangle would they create? Equilateral. And then we have the circumcircle and the incircle. All right, so the maths that we do, okay, these images are relevant. They happen in the real world, okay? And here we have the centroid. Okay, and the reason why it's centroid because it is a center of gravity. Okay, so the way we create the centroid, you get the perpendicular bisector of one side, and where it crosses, you go to the opposite vertex. Okay, get the perpendicular bisector of another side, where it crosses, you go from there to the opposite vertex. And then, so that's like blue Peter, what we've done earlier, and there we have the center of gravity. Okay, at the centroid reservoir. But anywhere else, it falls off. And what do we know about the centroid in terms of the ratio from this side to this side? What's the ratio? 2 is to 1. Okay, so the ratio here, the medians are divided in the ratio 2 to 1. Right, so here we have the Bermuda Triangle. Right, I want to get from Bermuda to Miami. Is it quickest to fly direct or fly around the other side? What theorem was it we found here?
Two sides of a triangle together ratio is right.
So there's a theorem, 2 sides of a triangle are together greater than a third. Right, so the theorems we use are relevant. Yeah? Things we might logically see. Okay, here we had, right, what types of lines do we see here?
Transversals and right-angled triangles.
So you've got transversals. So transversals because they're crossing what type of line?
Parallel lines.
So these are parallel lines, and then you've got the transversals crossing the parallel lines. And what does the theorem tell you about the transversals crossing parallel lines?
That they cut them in equal ratio.
So if they cut one set in equal ratio, they cut the other. So if these are both 270, what must both of these be? If one's 240, the other one's also going to be 240. Okay. So here we had the 3 deck chairs. Which set? Set chair 1, chair 2, or chair 3 would be the best one to sit on, do you think? Chair 1. Why chair 1? It's got the widest space. So we have a triangle here. What do you know about the longest side of a triangle? The longest side of a triangle is? What do you know about? Is there any theorems? It's going to be opposite the largest angle. Okay? Here, do we have this image, anyone? Yeah, what do we find here?
2 triangles are similar, then
Yeah.
the sides are proportional.
If 2 triangles are similar, then the sides are in proportion. Here, with a golfer. Right, tangent to a circle. And then here, what types of shapes do we have? Parallelograms. What do the theorems say about parallelograms? The area is the base by the height, and then also, right, diagonal bisects the area. So they're images, sort of the theorems that we use to, but we're putting them into context. Right, the Louvre. Here we have the Louvre. What do we say about the Louvre? The base times the height, yeah, does not depend on the choice of base. Is that fair enough? And here we have, right, so there's a man looking down at a mirror, finding the height. So what do we have here?
The triangles 4 times bigger.
Yeah, because they are going to be important. Yeah, similar. Now that's quite nice. So we've all used the chronometers. We've all been outside with the students at this stage, measuring the height of the school building with them. This is another nice activity as well with similar triangles. Right, so we've done shadows as well. A lot of us have been outside measuring shadows for goalposts and things like that. Another one we can do is using the mirror. So say if we know one person's height in the classroom, find another student's height, have a mirror in the floor, let the student stand back until they see the height of the person's head. And that gives them 2 similar triangles. Okay, so it's another nice activity. Now geometry is there. It's been around for a long, long time. Okay, it's been, right, and archaeologists use it a lot as well. Because you know when they go on a dig, and they're there for a long time, digging out, sweeping things away, and they get very excited when they see some pot appearing in front of their eyes. And they dust away the soil slowly, and then they get a sad face. Because it's not a nice, full, beautiful vase. All they have is a shard of a vase, okay, a piece of a vase. But they want to try and reconstruct the full vase. So from this shard, so they've got a piece of it, right, they want to try and reconstruct it and find, right, so they've got shards, so it's not necessarily a semicircle or full piece, it's just a piece of one. They want to try and find the center of this shard so then they can reconstruct it and draw out the whole, know the size of the radius and diameter, circumference then, okay? So over to you now. So you have on your mats, take out your mat, you've got your mats there, take out a marker. What theorem, so look down through your theorems. What theorems might help you find the center of the shard? So you've got an arc. What theorems might help you find the center of this shard?
If you go, does that go to the center? If you do a tangent, yeah, it should.
Still it's 3, darling.
If we do another one.
3 terms go.
Yes, I think that's.
That's another nice we do the tangents first of all, and then point of contact, the line perpendicular to that line being centre. Then we do another tangents, perpendicular again, where they intersect. That diagram will where they intersect.
Perfect, that's perfect, okay. Right, so what's the other way?
If you do a chord and bisected, and another chord and bisected. Does that work?
Yeah. Okay, so it's perfect. No, it's the idea we're looking for. So in terms of using the theorems are relevant and they're used. So we have the perpendicular to a tangent, goes through the center. And we also have the perpendicular bisector of a chord, goes through the center. Okay, so the theorems are relevant. Now, how could we do it with the first years? Is this do any of you invigilate the exams in the summer? No? Invigilate, do you make the big box you get? There's different kinds of paper in the big boxes, aren't there? And some of that paper is never used. Now, there's isometric paper, things like that. Is there any other sort of paper that's in there that's never used? Tracing paper, right? Is in there, never used. But with your first years, you could use that. And here's how you could do it with your first years, which is a nice way. Now you see now in a second why, if you do this type of activity with your first years, here's an understanding. Now often we stand up with a circle with first years and put it on the board and write on a few words that we assume the students understand. Alright? Now if they do an activity like this, they might be able to gain more understanding about the different parts of a circle. Right. Now in terms of the syllabus, in terms of the circle, it highlights center, radius, radii, diameters, arcs, sector, circumference. If we do that type of activity, so often they're words that we throw up to first years, assuming they understand what they mean. Whereas if we do an activity like that maybe with them, they might then be able to label them and actually understand, what a sector is, what an arc is, all right? And gain some understanding that we're actually doing an activity, rather than some random words that mean nothing. And there's, so your theorem is each tangent is perpendicular to the radius, and then the perpendicular from the center to a chord, all right? And again, there's the understanding there. Okay, but you've seen all these done. Now these videos are all available online as well, so on the website. So that is the perpendicular. So what is it that's just been made there? Perpendicular bisector. How is it? Sheena's made that. How is it she made it? What did she do? She folded it over. Because what is the perpendicular bisector also? Axis of symmetry. So the perpendicular bisector is also an axis of symmetry, which we might use that fact later on today. And that idea of folding it over to create the perpendicular bisector. Right. Where they meet is the center. Now, so that's looking at geometry in context. So it's generally we've taught it as a very cold, very abstract sort of topic, whereas it is relevant, it is real for students. Now we're going to look at reasoning and proof on part of the course. Right? Now, the master of deduction was Sherlock Holmes. He understood about proof and why we need proof. And often, again, it's something we've given to students as just something that we do. We're doing proof. I know it's annoying students, but we have to do it. Rather than showing that there is a need for proof. Okay, so that's what we're going to do now. And there are different types of proof, but often we start with a few lines. A miracle occurs to the students. There's 2 lines that make sense, there's 20 lines that don't. And then we end up with a fudged answer. Okay? So we look at, there's 2 different types of reasoning. There's inductive and there's deductive.
Math gives us 2 different kinds of reasoning. Deductive reasoning and inductive reasoning. That's the part that we take away from math. Deductive reasoning is a series of connected logical steps that leads to conclusion. For example, if I don't hang out with my friends after school, I'll go to the library and study. If I go to study, I'm going to get an A on the test. If I get an A on the test, Mom's going to be happy. Therefore, if I don't hang out with my friends at the mall after school, my mom won't be happy. Deductive reasoning. We need that. We use that in everyday life. Inductive reasoning is where we look at data, we find a pattern, and we make a generalization based on the data. If I cram for my science test and get an A, If I cram the next day for my English test and get an A, hey, this is working, isn't it? Therefore, it works all the time. Now, that's not foolproof, but that is the kind of reasoning that we use. Math gives us those same kinds of reasoning. Here's an example, deductive reasoning in math. If 2x minus 1 equals 9, then therefore 2x must equal 10, therefore x equals 5. We all get that. But your math teacher gives you 20 million of those problems to do for homework the next day and expects you to make the inductive reasoning leap. Every time I see a problem like that, this is how I solve that. It's that leap, actually, which I find the most challenging as a math teacher. Not how to do one problem, but how to do them all that look kind of like that. But if there's a 0 next to the x, then the whole thing falls apart. So inductive reasoning doesn't stick all the time, but it is something we use all the time.
So the difference between deductive and inductive. So when we spot a pattern we think it's going to work, then we say, okay, that works for everything. It's your inductive reason, okay, but it may not always stick. Now, we have a look at reasoning. So here we have sort of some buildings we're going to look at a pattern for these structures here, okay? So here's 1 story, 2 stories, 3 stories. I'm going to try and see if we can look at patterns, okay, to predict how many beams are needed for 12 stories. Now, how many beams are needed for 1 story? Now, a beam, okay, that's 1 beam, 2 beams, 3, 4, 5, 6, 7, 8, 9 beams. Is that fair enough? 9 beams there. This next one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 beams. Okay, so over to you now in your pairs. How many beams will be needed for 12 stories? Okay?
Yeah, but let's find a general formula.
Okay. So when your rate of change is constant, it must be a linear pattern. And then, right. So 7 times by 1 is? What's 7 times 1? 7. What do I add on to get to 9? 2. 7 times 2 is? 14. What do I add on to get to 16?
Plus 2.
2. So what's your formula? From your patterns, what's your formula going to be? 7s. So the number of beams is equal to 7s plus 2. Okay? So looking through your patterns. So we have a table. Yeah, remember a table needs 2 columns. We need our input and our output. What else could we have done with that table? We've graphed it. We've got a story. We have a table. What else can we do? We can graph it as well. Yeah, you can always sort of to get through the different things we can do. Now it says Callan has deduced that the formula for the number of beams needed for a tower with stories is given by this. His teacher says he's made 1 mistake in his deduction. Can you find Callan's error? What was 0? No, what's his mistake? Yeah? He's made 1 mistake. Is a story short? Yeah? Okay? He has it all up. So often we've seen these sort of problems arising now where students are given incorrect formula. So, right, what is the problem? What's wrong? So it's something they need to have experienced before and saying what's wrong. Now there could be various ways that could, maybe the 3s comes from the 3 vertical. The s plus 1 comes from the top and the bottom here. And then there's only got 1 s for the diagonal. Okay? Maybe. But the fact that what is wrong is that he's 1 story short. Okay? Right. But students believe that empirical argument means proof. They need to have a reason maybe to think differently. Traditionally, when they're seeing proof, it's like this. A very cold manner. Right, so on your mats now, I want you to pick 2 odd numbers. So on your mats, write down 2 odd numbers and add them together. Pick a different 2 odd numbers and add them together. Right, let's start to get a bit braver with the odd numbers we're picking. Okay, let's see how brave we can get with the odd numbers we're picking. Right, let's pick 2 bigger odd numbers and add them together. Go on, see how brave we can be. See who lives life dangerously. So what can we say happens when we add 2 odd numbers together? Even. And we say that whole, is that a fact? Can we say that's a fact now? So you've done it, right? We've all done, so we've got 8 groups here, we've all done 3 of them. Can we say that's a fact?
Well, the students will say it's a fact anyway.
That's it, right? But can they say it's a fact?
No.
No. Because what type of thinking is that? That's an inductive approach, yeah? To say, so we can't say through that manner we'd have to do every pair of odd numbers, okay? To have it work out right. So we can think it's true, but we can't say it as a fact it's always true. I'm going to have a look at that now. If you turn to page 4 of your booklet, right, there's a task we're going to do now. Right, so we'll talk you through it now. If you hold on for a second. So on page 4, we're going to put different points on the circle. I'm going to join them together. So every point must join a point. So for the first one, the top left circle, put 2 dots on the edge of the circle, please. And join the dots together. Anywhere around the circle, put 2 dots. And then number the regions. So how many regions do you have? 2. Right, so 2 dots on the top left circle. Now the booklets are all available for you to download on the website. They're all there to download. All right. The next circle, 3 dots. And every point joins every point. So every point joins every point. So the next circle joins 3 dots. And see how many regions we have there? So every point joins every point. And then keep flying then. Every point joins every point. Okay? Yeah. So once you finish page 4, go to page 5. So work in your pairs, try and get a formula in your pairs if you can. Try and work out a rule. Once you've done the table, try and work with your table, try and get a pattern from the table. On page 4, try and get a pattern from the table. See if you can work out what's happening on the table. So that's 8 points. Okay. What's happening here all the time with these numbers? They're doubling, so we're multiplying it by?
2.
Okay. Right, now, let's think. This is 2. So if I want to write that as 2 to the power, what's that? 4. What's that? 4. 2 to the power what? 2. So let's just write next to it. It's going to help us in a minute. Okay. Right. So that's 6. That's 3. It's 2 to the power 2. 4 is 2 to the power 3. 5 is 2 to the power 4. So what are we doing to this number every time?
1 less.
1 less. Yeah. So if this is 7, so if it's 10, it's going to be 2 to the power of
6.
Yeah, so
it's 1 less.
1 less. So 7 is 2 to the power 6. 8 is 2 to the power 7.
Yeah.
If it was 20, say this is 20, 19. If it was n
minus 1.
At 2 to the power of n minus 1. Okay, that's what we're thinking. Okay, so let's keep going and have a look at the next page. Okay.
Okay, it's 1 away. No. Well, that means 4.
Yeah. Go to magnify that. We have to. Yeah. Okay. So. No.
I suppose if it was slightly inaccurate, it could end up being a point.
Yeah, because you always say with a magnifying glass you zoom in and zoom in and zoom in. If you have it like as a regular hexagon, then it will just be a point in the middle.
Yeah.
What type of thinking were we doing? Inductive. So is there a need to prove things? Yeah. So the idea of that task is to demonstrate there is a need for proof. We can't always assume inductively that the rule works. Right? For the stories we knew when we did the building, we knew things weren't going to change. We're going to be adding on 7 every time. The rate of change was constant. But here we didn't know what was going to happen. Okay? So when should students begin to look at the idea of mathematical proof? In a student's experience at school, when should it be? And what area has it been in, normally, that they met proof? What area of maths? Right? Geometry. Maybe what year?
Probably 3rd year.
3rd year, just either before the mocks or just after the mocks, around then? Yeah? There's been the traditional sort of approach. When do you think the department says students should meet proof? Right. In your syllabus, on the common introductory course, under the number strand, it says, begin to look at the idea of mathematical proof. Okay, so under number, right, through looking at numbers, students should meet proof. Okay, that might help students understand what proof is. Rather than just being something that's very cold in geometry, okay, it does come across the strands as well. So here's one that we're going to have a look at now. It looks like every odd number greater than 1 can be expressed as the sum of a power of 2 and the prime. So let's think. So the first odd number, right? Every odd number greater than 1. So the first one is 3. That's 2 to the power of what? 2 to the power of 1 plus 1. Does that work?
No.
No, because 1 isn't a prime. So 2 to the power of what? 0 plus 2, because 2 to the power of 0 is 1. 5. 2 to the power of?
1 plus 3.
Yeah, 2 to the power of 1 plus 3. Have enough of that?
Yeah.
7.
2 to the power of 2.
2,
3.
3. 2 to the power of 2 plus 3. Or it could have? 2 to the power of 1 plus 5. Yeah, so there's different ways we could do it. Okay? And so generally we'll start off with the highest power. And if it doesn't work, we'll try another power below it. So it looks like any odd number can be written as 2 to the power of a number plus a prime number, okay? Can we say it holds true forever? What type of thing would that be? Inductive. So at the moment, can we say it holds true forever? No. Now, what I want you to do in your pairs, pick one odd number between 9 and 49. Pick another one between 51 and 99. And then pick another one between 101 and 149. So pick any odd number in those 3 strands and see if you can
Choose the each of us. Oh no, that's not much. 2 to the power of 7. Yeah, 2 to the power of 7 plus 3.
Perfect. So if 2 to the 5 doesn't work, you try 2 to the power of. It's not 2 to the first number, try 2 to the power of.
6, but that goes
So try 2 to the power of 4.
Okay, so no.
2 to the power of any number.
Okay,
it's not, yes, we're not restricted to the highest power. Okay? Does that make sense?
Header says
Yeah.
16, 25.
Yeah.
Okay.
Yeah. One very quick way to check if there's a prime number or not for your students is your prime factor button on your calculator. So got 1, 2, 3. So is 123 prime? So type in 1, 2, 3 in your calculator. Press equals. You see here on your calculator, see fact. That finds your prime factors for you. So you type in your number, you press equals, then because it's in yellow, what do you got to press first? Shift. Okay, so is 123 prime? No, is that make, so you, no, is that make, so it's a very, very handy way of finding your prime factors. Okay? Alright, so if you get one that doesn't work, the first one that doesn't work, right, maybe, I've done this workshop about 20 times, I think 5 times I've had somebody pick the number between 101 and 149. The first one that doesn't work, the first counter example is 127. Okay? So the first one that can't be written as 2 to the power plus a prime number is 127. Okay? But it's a nice activity. I think it's a great activity for your class, not only just for the idea of proof, but just for revising powers of 2 and prime numbers. There's a lot of revision done in doing that one activity. You're ticking 3 or 4 boxes at the same time. It's a very nice activity. Now, I think you've earned a cup of tea, okay?